Hey everyone, welcome back, and today let's solve Leetcode problem 47, titled Permutations Part 2. So similar to the first problem, we're given a collection of numbers, nums, but in this case it might contain duplicates, and we want to return all the possible unique permutations in any order. So in example 1, we have our input array nums to be 1, 1, 2, and of course all the possible unique permutations would be 1, 1, 2, 1, 2, 1, and 2, 1, 1. Right? So similar to that kind of recursive or backtracking idea with all the unique or different permutations from the input as we saw in the first part of this problem. However, there is a little bit of a twist because we are also guaranteed or given the possibility that it might contain duplicates. In example 2, we have our input array nums to be 1, 2, 3. Something important to note is that it is actually sorted, which will actually help us because we see we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1 as all of our unique output permutations, right? So for the constraints here, we see that the length of our input array nums is actually going to be less than or equal to 8 at most, and every value is going to be within negative 10 and 10, right? So that kind of brings us to the main observation and what we really need to kind of know to really be able to solve this problem, right? How can we actually efficiently generate all the unique permutations? Again, it really is just a build off on Leetcode. I don't remember the problem name, but the previous permutations problem, Permutations 1, right? We're still going to be using that backtracking and recursion approach, but it's going to have a slight twist, right? Why do we have a slight twist? Well, because we have the possibility that our input might contain duplicates, right? So how are we going to kind of use different algorithms and leverage them to our advantage? With these duplicates, we're actually going to be using sorting. Why do we want to first sort the array? Well, because it will help us in actually identifying all the duplicates easier, because all the duplicates that appear multiple times or have more than one frequencies would be next to each other, right? And so once we actually sort the array first, then we'll actually use backtracking with the used array. So we're going to have a Boolean array. I'm just going to call it used. And as the name suggests, it's going to keep track of which elements we've already used as part of our current permutation to make sure that whenever we're actually trying to add or not include elements in the current permutation, we haven't used them yet, right? And we're sorting them because we know that we'd always get each value that are adjacent to each other that are equal or duplicates, and so we don't have to worry about them later on, right? So we're sorting them for all the easier version to get all the duplicate values together, and then we're going to use that used array to check if we've used a value before, if we again encounter its duplicate, right, to avoid any duplicates in our output, right? So again, when choosing an element, we have to skip it if it's a duplicate and if it hasn't been used in the current recursive depth or current permutation that we're building. And for the actual kind of main recursive part, we'd explore each valid choice, we'd build the permutation, and we'd backtrack when needed, as you saw in the first part of this problem, Permutations 1 as well, kind of the standard recursive approach, right? So we're going to have a used array to track all the selected elements for all the different permutations that we build. We'll have a path list to actually build our permutations incrementally in each iteration or call recursively of this function, and a resulting list that's going to store all of our unique permutations of that specific length input array nums, right? So let's go ahead and get into the code here. So what am I going to do is I'm going to actually initialize my result like I usually do for backtracking problems. This is going to store all of the unique permutations, and like we talked about just now, I'm going to first sort the array. So I'm going to call the sort method nums.sort on our input array nums, so it will actually make it a lot easier to handle the duplicates because all of the duplicate numbers would be adjacent to each other, making them a lot closer, and so we can also skip them or use them a lot more easily and a lot more efficiently as well. And like we just talked about, we'll also get that used array, and for all the values, initially they'll be all set to false because, of course, we haven't actually used any values just yet before actually starting this code or software, if you will, right? And we're going to multiply it by the length of our input array nums, right? That's basically going to be its dimensions. It's going to have the same number of elements as our input array because it's going to track a Boolean value for each element in the input array to check whether we've used it or not, right? We're checking more to kind of elaborate, keeping track of which elements that we've actually used in the current recursive call for the current permutation that we're building of the current recursive function call, right? So now let's actually initialize our backtracking function. Sorry about that. Like I usually do for backtracking problems, I'm just literally going to call it backtracking, and we're going to have one parameter, right? It's going to be that path. You could also call it something else. You could call it current or current permutation. Really, this inner function backtracking is going to have a list path. That path is going to represent the current permutation that we're currently building, right? And we're going to actually call this function within itself recursively to build all those unique permutations while skipping any duplicates that we've encountered before, right? So like we usually do for backtracking functions, we're always going to have our base case first. And in this case, we have a very standard base case for these backtracking recursive problems. If the length of our current path, basically that means the length of our current permutation, if it's equal to the length of our input array nums, we've used that many current elements, we've kind of built one full or we formed one full complete permutation, and so we're going to append it to the result. So result.append the current path copy, because we don't want to change any elements and then override it when we actually append it to the result, and then immediately return for this current call and move on to the next call. Right? Very standard base case. If the path has the same length as nums, it has that many equal elements, we've formed a complete permutation in the current path, we'll add a copy of it to the result, and we'll immediately return for this current call of the function. Right? Now, if we haven't actually hit our base case yet in this current call or iteration of this function, let's actually start choosing which elements to actually skip or actually use based on if they're a duplicate or not in our input array nums. So let's actually iterate over our input array nums. So for I, the range of the length of our input array nums, and this problem could also be solved using or taking in I index as a parameter, but I think that kind of overcomplicated. So if used at I is equal to true, and a simpler way to check that in Python is if used at I. That means, very simply, we've used the current element. It is a current duplicate. We don't want to use this duplicate again, and so we're going to skip these already used elements, right? It's already part of our current permutation. It is a duplicate. We don't want to include it again as a duplicate permutation, and so we're going to skip it. How do we skip it? Well, we simply continue on to the next iteration, or in other words, in this for loop, the next element. Now, if we haven't skipped it, or rather, if we haven't skipped it, if we haven't already used it in our current permutation, we want to then use it, right? So the way we can do that is if I is greater than 0, and the current element if it's equal to nums at I minus 1. Why do we care about the previous element? Because we want to make sure that it isn't a duplicate. So as long as it's not equal to its previous element, and we haven't used it, so we haven't used nums, rather, I think, okay, we haven't used nums at index, oh my god, sorry about that, guys. Not used I minus 1, sorry. I don't know why I had nums in there, but if we have not used the previous element, only then can we still continue, right? Because this is kind of the second duplicate portion using that sorting factor for this, right? That kind of is another observation to really make, right? If two consecutive numbers are the same, we only have to consider its first occurrence, or when the previous duplicate has already been used, right? Where we're checking right here. Right? So effectively, we're basically ensuring that we don't generate any duplicate permutations as a whole. So as long as I is actually in bounds, right, we don't have an inbound or out of bounds error. And the current element, if it's actually equal to the previous element, and we haven't used the previous element, we only want to care about the first occurrence of the duplicate values. We don't care about the other element because we don't want to have any duplicate permutations that we build and add to our result, right? So if that's not the case, if either one of these conditions are true, we immediately have to continue. However, if that's not the case, we haven't continued yet. Now let's actually use the current element because it does actually kind of pass and validate all the checks. So we'll get use at I and mark it to be true. Why? Because we're essentially simulating to be using it in this iteration, marking this number as used, and now appending it to our current permutation, or in other words, our current path. So we're adding the current path, rather the current element to the current path, or current permutation that we're building, and we're going to recursively build that permutation, calling the backtrack with the current path based on whatever elements it has, right? And now for the actual recursion part, we're going to have a path.pop to kind of clean up what we did in the recursive call, and when we added nums that add to the current path on lines 16 and 17, and once we actually remove it, or remove the last element to backtrack, we then have to remove that element or mark it as false, meaning we haven't used it anymore because we're removing it from the current permutation. Right? We're unmarking the number so it can also be used in other permutations, simulating that kind of removing last element or backtracking element. Right? Effectively, again, here we're simply marking the current element as used if it did actually pass these conditions and it is actually a valid number to be used. It isn't a duplicate or anything like that. We add it to our current permutation or path. We make a recursive call to backtrack to actually continue recursively building this permutation for all valid indices that we choose to skip or not. And then for the actual recursive part or the undoing part, after we actually explore all the possibilities with the current number, we then have to backtrack by actually removing or path.popping, right? We're removing the last element from the path and marking it as unused again in the used array, right? That's the main undoing a recursive part of logic of this method, right? And effectively, now that we're done with the actual function here, let's call backtrack to make sure that our entire list is actually completed fully, right? So we're starting the recursion with an empty path, right? So I'm going to pass in a list as an empty path. This is the initial permutation that we're starting off with. It's empty, right? And effectively, we simply have to return the result, because once this backtracking method is done being called, once it's done executing, the result would actually store all of the unique permutations when we add all the different paths or unique permutations to it when we fully complete them, right? That's going to contain all the unique permutations of our input array nums, right? When we actually call the backtracking function, starting with an empty permutation and building off elements from there based on if we can actually skip them or not, and based on if they're actually going to contain duplicates or duplicate permutations or not. So if I were to submit this, unless I made any syntax errors here, there should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So on a high level rundown again, how does this solution really work? We're first sorting the input array. That makes all the handling duplicates a lot more easier, because all the duplicate values would actually be adjacent or next to each other. Then we actually use this backtracking or recursive approach like we did for the first part of this permutations series of problems. And we're also doing this with a slight tweak, using that used array to make sure that each element in our current permutation, it's only being used once, and we're always skipping duplicates a lot more efficiently and in a very kind of creative way as well, right? So we always only generate the unique permutations in the most efficient backtracking manner, because backtracking isn't really known to be the most efficient solution, because we have to actually explore all the different possible choices, so it's known to be very slow. But either way, it is really just about as efficient as you can get for the context of this problem, which brings us to the complexities of this solution. For the actual runtime complexity, the overall runtime complexity would be big O of n factorial times n. N factorial would be actually the number of permutations that we account for in our backtracking method, and n would be the list copying operation in each path or complete permutation of our backtracking method when we actually add it to the result. And for the memory or space complexity, it is also big O of n factorial. Why? Because we're actually storing all those unique permutations in the result list, and we also have that big O of n linear space for the recursion depth, and we also have the used array, which is another extra data structure, takes auxiliary memory, and so the overall fully simplified bottleneck runtime complexity would be big O of n factorial times n, and the memory or space complexity fully simplified would be big O of n factorial. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.